Hello and welcome everybody. My name is David Reed. I'm a current PhD student at CWC in the University of Oulu, and I'll be your host for this new video of 5-minute paper series. This paper is entitled Energy Efficient Wake-up Signaling for Machine-Type Devices based on traffic-aware long short-term memory prediction, and it's available in the link below in the description of this video. Well, to start, let's say that supporting and driving a large variety of devices is a need in future networks, where one of the main challenges is maintaining the availability of the devices for several years without battery recharging or replacement. In that sense, energy efficiency is a key design requirement due to the limited energy resources present in those devices, being the monitoring of the idle channel one of the major energy consumption resources, particularly in networks with low traffic. We can say that one promising approach to prolong the lifetime of those devices beyond 10 years was the one introduced by the third generation partnership project in the release 15 called Wake Up Radio. Basically, during the sleep mode, the device waits for the reception of some regular paging events to decide whether to switch to active mode, which is of course more energy expensive, since monitoring those paging events is almost as costly as being in active mode. With the introduction of this wake-up signal by the wake-up radio, the paging events are preceded now by the transmission of a narrowband wake-up signal, which allow the device to remain in a low power state by default and only wake up to the code, a paging event, or an occasion if the wake-up signal is identified. So, in this paper, we aim at designing a wake-up signal mechanism enabled by an efficient artificial intelligence predictor to reduce energy consumption. Specifically, we leverage a simple neural network to predict machine-type communication traffic patterns and configure a wake-up signal mechanisms accordingly to those predictions. Here we present the system model used considering a machine-type communication network where the coverage area of the base station is split in several smaller areas in which a coordinator controls and collects information from the devices. In this case, we can say that the devices are equipped with a wake-up radio model to allow to save energy, and they are deployed using a Poisson point process. The traffic exchange between the devices and the coordinator or base station is modeled as a two-state complete Markov chain, where each device can be in one of two states. The idle state, which the device is waiting for a wake-up signal from the coordinator, or the active state when the device is exchanging information with the coordinator. By using the wake-up signaling, the device could be in four different power levels, as shown in the figure. The most power-consuming or active ones when the information exchange process is taking place. And then there are the idle ones or low power states when the device is either in sleep mode or monitoring the wake up signal. Now, configuring the wake up parameters, it's a challenging task since as we can see in the bottom left part of the figure. Properly configuring these parameters could avoid unnecessary monitoring, leading to save even more energy. For this reason, we propose in this paper a neural network-based traffic forecasting model and a methodology for properly configuring the wake-up parameters. Specifically, we use a long short-term memory network since this is especially designed to learn dependencies of different sequences. Then the wake-up parameters are configured based on the result of this predictor. The results obtained from the predictor show that after just 30 iterations, the error value remains almost constant at around 0.1, while it's been demonstrated that a high accuracy uh, is possessed to adapt to incoming data in the validation and the test processes. Now, for the power consumption, we compare our proposal with the standard wake-up signaling model and with the well-known discontinuous reception mechanism. In the left part of the screen, we depict the power consumption as a function of the number of devices for each mechanism. We analyze the results for different event densities that trigger the active state in the devices, represented here by lambda, and for different worthiness of the traffic that is represented here by Q. Note that our proposed scheme, the orange one, outperforms all the others, while the energy saving with respect to the standard wake-up signaling becomes even greater as the traffic volume increases. Now, on the right side, the figures illustrate the performance of our proposal. When the band density varies dynamically over a period of time, completely different from the approaches in the figure of the left side, where these parameters were completely deterministic. Specifically, in the right side, in the figure in the right side, we increase and decrease the event density. Uh, However, nevertheless, the proposed scheme is able to adapt itself to these variations. Well, to conclude, I would like to highlight the main points, contribution and results treated throughout the paper. First, we model an MTC, a machine-type communication network, using different and independent Poisson point processes. Second, we propose an intelligent wake-up scheme called FWuS to, to be used by the coordinator to reduce the energy consumption in the devices and prolong their battery lifetime. Third, the traffic forecasting relies on a simple neural network which achieves prediction accuracy results above 96% by monitoring the MTC traffic patterns. Fourth, we can say that the proposed model enables energy consumption reduction up to almost 35% to the competing scheme with the best performance, while the main delay increases only on 2 up to 6 milliseconds, but always below the 30 milliseconds constraint. And finally, we can say that the proposed mechanism was shown to be robust and adaptable to different traffic and scenario with dynamically changing parameters, performing well under any traffic variability. Well, that's all for this video, and thank you for your attention. And if you want to see more information about the paper, we left the links in the description below. See you in the next video of 5-minute paper series.